Similar fashion to Alex's project, I'm implementing virtual environments, but in this case, I'm looking at what happens to debris when it's disposed of between the top of the water, and what happens to it when it hits the ground. So what the path it's going to take. Just for a bit of background, I've done some co-op work with Environment Canada's Disposal at Sea group, and also just to give a background on this issue. So before the 1970s, oceans were typically used as waste dumps for solid and liquid waste. I mean, they're still used for liquid waste such as sewage runoff and that kind of thing, but the amount of solid waste that's being disposed in the oceans is arguably a lot less, at least in more developed countries that are part of this London Protocol here. All right. So the scientists at Disposal at Sea and concerned citizens in these coastal communities that would be most directly affected by the dumping of garbage and things like that, they would benefit from a tool like this, which is inexpensive and an effective way to visualize these disposal sites in 3 dimensions. And the main idea behind this project is that ocean environments are typically out of sight and out of mind. So what I'm trying to do is remove the veil of the ocean surface and let you see what actually happens once things are dumped into the water. And why would I do this in 3D? I mean, people do current models already in 2 dimensions. A 3D visualization, more so than a 2-dimensional map, really sort of engages your cognitive processes that you would normally, like, for pathfinding. Like you, instead of looking at a map and trying to find out where to go, you see and write the direction you're supposed to go, and you can use similar features to situate yourself. And this is my first sort of foray into integrating visualization and computation in 3 dimensions of a 3-dimensional phenomenon. And the biggest issue that people have when they're thrown into a first-person view in a virtual environment like this is that they get lost. So that was one of the main things I tried to do with this project, and I did that through an interactive mini-map, as well as I will show you in the next slide. I rendered what's called a skywalk. So this lets people use the North Shore Mountains to situate themselves, because as we all know, living in Vancouver, you get lost. Where do you look? You try to find the mountains. That's north. All right, I'm going to need my lovely assistant Alex in a second here. So for the sample scenario that we're doing here, this is a representation of the currents. This would be facing through there, would be facing Vancouver. Also north is that way. This is a work in progress, and my interface isn't as developed as Alex's is. Right now, we want to look down and left, up. As you can see, people do get lost. So this debris is being acted on by currents as it's going down to the bottom of the water. And this gray thing here is something else that I have to work out. It just came up last night, actually. But see, as you can see, this gives you an idea of the distribution of the debris based on the currents. So one level of debris was pushed into a different current system first, so it was pushed out before the other ones were, which led to more of a spread at the bottom. And it's also important to note that even though you don't notice much curvature there, the currents I've used are fairly weak, but it's fairly easy to customize them to be much stronger. And I would just like to thank formally the Canadian Hydrographic Service for providing me with this very high resolution bathymetric data. This is a bad example of the resolution, but let's just ignore that. I would also like to thank Nick Headley for his guidance throughout the project, as well as the rest of my Geography 457 colleagues for their technical and moral support, because you spend long hours in that lab.
Thank you, Nick.